Hello, my rubber hearts. Today we are opening another drawer in our Rubber Technologist toolbox, and this one is all about dynamic behavior, the way rubber comes alive when it's moving. In Season 2 we talked about DMA and tangent delta, and how that little ratio tells you how efficiently your rubber stores and returns energy. But out in the everyday rubber world, especially in factory labs, you don't always have DMA. What you do have are classic dynamic tests that production labs have trusted for decades and that every rubber technologist eventually learns to use. Rebound resilience, heat buildup, and flexometer testing. So today we are going to connect the elegant theory of DMA with the practical tools you will actually see in industry. Rebound resilience looks deceptively simple. You drop a hammer onto a rubber specimen and measure how high it bounces. High bounce means the rubber returned a lot of energy. Low bounce means it ate that energy as internal friction. But to really use rebound as a meaningful measurement, you have to understand that rebound is a temperature-dependent story. Just like tangent delta, rebound shifts dramatically depending on whether the rubber is cold, warm, or hot. The machine itself is straightforward. There's a striker, a drop height, and a sample, usually a little cylinder or disc. But the sample handling is where young technicians run into trouble. Rebound testers with built-in heating plates or cooling mounts are helpful, but they heat or cool the outside of the specimen faster than the inside. If you want clean, trustworthy data, you precondition your sample in a temperature-controlled oven for hot testing or in the freezer or cold chamber for low-temperature rebound. And you give it enough time to stabilize through the entire thickness, because surface temperature alone is not enough. Then comes the choreography. You remove the sample, mount it quickly, and test immediately. You don't touch the test surface with warm hands. You don't squeeze or press the specimen while placing it. You don't wait 30 seconds chatting about something else while the temperature drifts. A good rebound test is really a demonstration of disciplined, repeatable handling. Now, the real beauty of rebound is that it tells you different things at different temperatures. At low temperatures, it tells you how the rubber behaves as you creep closer to the glass transition, and whether it's going to feel stiff or lively in the cold. At room temperature, it gives you a general sense of damping and vibration behavior. And at high temperatures, particularly 60 to 70 degrees Celsius, the real operating temperature of a rolling tire, it becomes a quick, practical indicator of rolling resistance. High rebound at 70 degrees usually means low tangent delta at 17 degrees, which usually means lower rolling resistance. That correlation completely disappears if you only test at room temperature, which is why rebound must be temperature controlled if you want to talk about real dynamic performance. Heat buildup and flexometer testing are where rebound's simple intuition grows into full-blown dynamic engineering. These machines load the rubber the way life loads it. A flexometer clamps a small specimen, applies a static preload, and then flexes it rhythmically thousands of times, measuring the heat the rubber generates inside itself. This is the physical manifestation of hysteresis. If your compound has high tangent delta or low dynamic efficiency, it warms up quickly. If it's well designed, the temperature rise is slow and the final equilibrium temperature is lower. Setting up a flexometer test is its own discipline. The specimen has to be perfect. No voids, no bubbles, no trimming defects. It has to be conditioned to lab temperature, so the test starts from a known baseline. It must be aligned exactly as the standard describes, because even a small misalignment changes the internal strain field and therefore the heat generation. If the standard calls for preconditioning cycles, you have to run them. Skipping preconditioning changes the entire heating curve and makes your results meaningless. Flexometer machines usually read the temperature through a thermocouple embedded in the specimen or pressed against the surface. That reading tells you two things: how fast the rubber heats and where the temperature stabilizes. A material that surges upwards and levels off high is burning energy internally. A material that rises gently and levels off lower is dissipating less energy. In other words, it behaves like a lower tangent delta material in real life. Heat buildup tests follow the same logic but with different geometries or loading styles depending on the equipment. The same rule applies. Consistency is everything. Same dimensions, same conditioning, same load, same displacement, same cycle count. This is where everything connects back to DMA. What you saw on the DMA curve, those peaks, those slopes, the tangent delta, now shows up as real motion and real heat. Rebound is the fast, practical cousin of the DMA. Flexometer testing is DMA translated into life under load. Heat buildup is DMA translating into survival or failure. And that is why dynamic testing deserves its own place in our toolbox. Static properties tell you how the rubber behaves when nothing is moving, but dynamic tests will tell you how it behaves when everything is moving, when the part is alive, vibrating, flexing, bouncing, and heating. A rubber mount stays quiet or starts buzzing because of dynamic performance. A tire wastes energy or rolls efficiently because of dynamic performance. A roller stays cool or overheats and cracks for the same reason. So remember, my rubber hearts, every compound has two voices, the static voice and the dynamic one. Today you learn how to listen to the dynamic voice, whether it's whispering through Rebound, humming through a flexometer, or shouting through a heat buildup test. And in the next Toolbox episode, we'll keep building your confidence in these real-world performance connections so you can choose and tune your compounds with purpose.